All right, so today I'm going to talk about basically equilibrium as it applies to acids, bases, and salts. About 1.4% of the solute molecules in a 0.1 molar acetic acid solution are ionized at room temperature. The remaining 98.6% of the acetic acid molecules stay unionized. So the solution contains three species of particles in equilibrium. You have acetic acid molecules, you have hydronium ions, and you have acetate ions. The equilibrium constant for this system is expressed at equilibrium ratio of ions to molecules. So we have our overall equation. It is helpful to note that the water in this example is a liquid, so it is not included in the equilibrium expression. So again, we've got products over reactants. So that becomes K equals hydronium times acetate over acetic acid, and then this becomes 1 because it's a liquid. At a 0.1 molar concentration, the water molecules are much more than the number of acetic acid molecules. And you can assume that the molar concentration of water molecules stays constant because it's a liquid, and because K and H2O are both constant, the product of K and H2O is also constant. So we can move the water to the other side. So we simplify the expression K times the concentration of water as Ka. So it's just basically the equilibrium concentration, equilibrium constant of the acid. So the A represents acid. This is called the acid ionization constant. Ka, like K, is a constant, is constant for a specific temperature. And if temperature changes, then the value of K will change. Ka for a weak acid is a small value, which makes sense because if you think about the concentration of acids in general, let's see, we've got HCl, yeah. Oops, sorry, plus H2O, H3O plus Cl minus. So this is an example of a strong acid. And if we were to write Ka for this, we would write hydronium over, hydronium times chloride over HCl because it's a gas, so it still counts. And just think about, as a strong acid, we have only the forward direction. So the equilibrium constant for a strong acid is going to be very high because at equilibrium, basically you won't even have equilibrium because it only goes in the forward direction. So this basically doesn't exist. So you just have H3O times chloride. But if you've got a weak acid, like acetic acid, H3O plus acetate, and you're going to have, like I said in the beginning, in this solution, only 1.4% ionizes. The other 98.6% is non-ionized, which means most of the species in the solution are going to be these two, which go in the denominator because it's products over reactants. So if we just pretend like if we do say 100%, the products in this case are the things that are ionized. So that would be 1.4 over the things that are non-ionized, which are the reactants, which is 98.6. This is why weak acids have a small Ka. And you can basically tell the strength of an acid based on its value of K. If K is a high value, then the acid is strong. If it is a low value, then it's weak. So to determine the actual value for Ka for acetic acid at a specific temperature, the equilibrium concentrations of the hydronium, the acetate, and the acetic acid must be known. The ionization of a molecule of acetic acid in water yields 1 hydronium ion and 1 acetate ion. These concentrations can be found experimentally by measuring the pH of the solution. If you remember all the way back to when we used to do this, based on the pH, we could calculate the concentration of hydronium and hydroxide. So that's how we get that. And based on that, you can see that the value of Ka doesn't really change that much over the molarity. So look at how the molarity is changing. Excuse me. So we go from 0.1 all the way down to 0.001, and the only difference is 1.79 times 10 minus 5 to increase to 1.82 times 10 minus 5. So it's only a 0.03 difference. Ka is almost identical for every solution molarity that is shown here. Even though we go percent ionized 1.33 all the way up to 12%, Ka doesn't really change that much. At a constant temperature, increasing the concentration of acetate through the addition of sodium acetate disturbs equilibrium. This would be equivalent of increasing the concentration of one of the species in the equation. So again, if you've got CH3COOH plus H2O, hydronium and acetate. So one way to disturb equilibrium is something called the common ion effect. It was a little bit at the end of the last section, which I skipped. The common ion effect basically is a way to shift equilibrium by introducing a substance that includes the ion that is in the equilibrium system. So for example, if we add the salt sodium acetate, that's going to be basically adding sodium, which doesn't have an effect on equilibrium, but adding acetate does affect equilibrium because you're increasing the concentration of one of the products. So it's going to disturb equilibrium and you're going to have a shift to the left. So that disturbance causes a decrease in hydronium and an increase in hydroxide. Eventually, equilibrium will be reestablished with the same value of Ka, but because you've shifted to the left, you're going to have a lower hydronium concentration than before you added the sodium acetate. So this is another example of Le Chatelier's principle. Changes in hydronium have a direct effect on pH. Because the H3O in the previous example decreased, it means that there is an increase in pH because hydronium is an indication of the pH. The more hydronium you have, the lower the pH you have because it's more acidic. So you can use this in something called buffers. The previous solution contains a weak acid and a salt of the weak acid. So we had acetic acid and sodium acetate. This solution can react with either an acid or a base. When small amounts of weak acids or weak bases are added to this solution, the pH remains nearly constant. This is called a buffer. The weak acid and the common ion, which is acetate, act as a buffer against large changes in pH. So a buffered solution is a solution that can resist changes in pH. And I'm going to explain how it resists changes in pH. Let's say a small amount of acid is added to the acetic acid sodium acetate solution. Oops, sorry about that. So I've got CH3COOH plus water yields H3O plus CH3COO minus. Okay, so that's our equation. If we add a small amount of acid, what's going to happen? The acetate ions, which are here, are going to react with most of the added hydronium ions to form non-ionized acetic acid molecules. So if you add a small amount of acid, you're increasing the concentration of hydronium, which means the acetate is going to react with that excess and form acetic acid molecules. So you've got the reverse reaction happening, right? So you've added acid, which increases concentration of this. Acetate reacts with this to form non-ionized acetic acid. So even though you originally added more hydronium, which you would think would decrease pH, because the equilibrium is going to shift, right? If we just look at it based on a pure Le Chatelier level, if you add acid, you are increasing concentration of hydronium, which initially might lower pH. However, because of the equilibrium shift, it's going to shift to the left and form non-ionized acetic acid to use up that extra hydronium, and the pH will remain almost unchanged. Okay, so again, a buffered solution is a weak acid plus a salt of the weak acid. Oops. So that's a bit off, but that's supposed to be pointing to the hydronium. Now, let's say you add a small amount of base. What happens to the system? What the heck? Oops. Wanted to get back to that. I gotta write the equation again. Okay, iPad. Oh, there we go. My screen went black for a second. All right, so I just gotta rewrite the equation so we can see what happens based on Le Chatelier. Okay, if you add a small amount of base, you're basically adding hydroxide ions, right? So adding hydroxide ions, you're going to end up having those react with the hydronium to form the water. So even though you're adding hydroxide is going to react with hydronium, it's going to reform water. So then you say that the concentration of hydronium is decreasing, but because the hydronium is being used up by reacting with the base, equilibrium is going to shift to the right to replace the hydronium that's reacting with the hydroxide. So when equilibrium is reestablished, pH remains the same. So the hydroxide ions of the base react with and remove hydronium ions to form non-ionized water molecules. But because you've disrupted equilibrium by decreasing the hydronium concentration, the equilibrium is going to shift to the right to restore the concentration of hydronium ions. Okay, that doesn't really help. So a weak acid plus a salt of the weak acid is a buffer. The same thing happens with a weak base. A solution of a weak base containing a salt of the base behaves in a similar way. The hydroxide concentration and the pH of the solution stay constant with small additions of acids or bases. This is not to say that you can have a buffer and then add a concentrated amount of like sulfuric acid, and the pH won't change. It's small additions of acids or bases that it can withstand changes in pH. So here I have a buffer that's made of a weak base, which is ammonia, and a salt of the weak base, which would be anything containing ammonium. So in this case, it's ammonium chloride. If we add a base to this solution, what we're doing is increasing the concentration of the hydroxide ions, which is going to drive the equilibrium shift to the right to use up the excess hydroxide ions, and you're going to produce non-ionized ammonia and water. So pH is not going to change. If you add a small amount of acid, the hydronium from the acid are going to react with the hydroxide to form water. Then you're going to see a shift. Here we go. Then you're going to see a shift, because if you add an acid, it's going to react with the hydroxide, and it's going to decrease the concentration of hydroxide, which means equilibrium is going to shift to the right to replace the hydroxide that is being lost through the neutralization with the acid. Again, the result is the pH doesn't change. Now, this is one of the things that I talked about at the beginning of the acid and base chapter, is the ionization constant of water. Two water molecules react together to form hydronium and hydroxide. The equilibrium is created with a very low concentration of hydronium and hydroxide. If you don't remember, at equilibrium, each of them has a concentration of 10 to the minus 7. So multiplying, because these are liquids, you ignore them. So your K, again, products over reactants, but all of our reactants in this case are pure substances, so they are not included. So our KW for the ionization constant of water is hydronium, which is aqueous, times hydroxide, which is aqueous, and that is equal to 1 times 10 to the minus 14. That was the basis for being able to calculate concentrations of acids and bases, the hydronium and hydroxide concentration, and then also the pH and pOH. All right, the last thing is the hydrolysis of salts. Salts are formed during the neutralization reaction between Bronsted acids and Bronsted bases. When a salt dissolves in water, it makes cations of the base and anions of the acid. You might expect the solution to be neutral because it is formed through neutralization reactions. Some salts, like sodium chloride and potassium nitrate, are indeed neutral. But however, when sodium carbonate dissolves in water, the solution turns red litmus paper blue. Ammonium chloride in water turns blue litmus red. This indicates that not all salts are neutral. So the question is, why? This variation in pH can be explained by looking at the ions formed when each of these salts dissociates. If the ions that are formed are from weak acids or bases, they're going to react with a water solvent, and the pH will have a value higher than 7. This is called hydrolysis. It's a reaction between water molecules and the ions of a dissolved salt. If the anions react with water, the process is called anion hydrolysis, and the solution is more basic. If the cation reacts with water, the process is called cation hydrolysis, and the solution is more acidic. So let's look at anion hydrolysis. The key of hydrolysis is understanding how conjugates work. The anion of the salt is the conjugate base of the acid from which it was formed. Hopefully remember conjugates. So for example, let's take ammonium chloride as an example. So this is the anion. It comes from the acid. The acid it comes from is HCl. If HCl is a strong acid, then the conjugate base is weak. So this is a strong acid. So this is a weak conjugate base. The ammonium, however, comes from ammonia, which is a weak base, which means ammonium is a strong conjugate acid. That's why you have to analyze the strengths of the acids and bases that the ions are formed from. In this example, if the salt is made of a strong conjugate acid cation and a weak conjugate base anion, this salt is going to dissolve in water, and the solution is going to have a pH less than 7 because of this. If, however, you have, sodium carbonate, I think was the other example. So looking at the acid and base that these ions were formed from, CO3 comes from carbonic acid, which is weak, which means CO3 is a strong conjugate base. Sorry, I'm kind of writing around the edges here. The sodium comes from sodium hydroxide, which is strong, which means the sodium is a weak con acid. So you put a salt together where the cation is a weak conjugate acid and the anion, did I say that? Cation? Whatever. The cation is a weak conjugate acid. The anion is a strong conjugate base. So the pH is going to be greater than 7 because of that one. If the acid is weak, the conjugate base or the anion will be strong enough to remove the protons from some water molecules to form hydroxide ions. Equilibrium is created where the net effect of anion hydrolysis is an increase in the concentration of hydroxide of the solution, which is more basic. I think I explained it a bit more clearly before. So let's look at another example of a salt. Let's take salt as an example of a salt. If I ask you, what will be the pH of a solution of sodium chloride? The only thing you have to do is analyze the acid and base strength that formed these ions. So where did Cl come from? HCl. HCl is strong, which means Cl minus is weak. It's a strong acid. Cl is a weak base. Sodium came from sodium hydroxide. Sodium hydroxide is a strong base, which means Na is a weak acid. If your ions, your cation is a weak conjugate acid, your anion is a weak conjugate base, that solution will be neutral. If you have, for example, let's do NH4 2CO3. CO3 comes from carbonic acid, which is a weak acid, which means CO3 is a strong conjugate base. Ammonium comes from ammonia, which is a weak base, which means NH4 is a strong conjugate acid. So here we have a strong conjugate acid with a strong conjugate base. That solution will also be neutral. It's only when you have, sorry, I think I'm just going to skip the text because I think I can explain it easier. Another blank screen. Here we go. Nope, blank screen. All right. If I've got sodium acetate. Ooh, that's a terrible color, isn't it? Let's just do black, make it easy. Sodium acetate. Okay. So acetate comes from acetic acid, which is a weak acid, which makes acetate a strong conjugate base. Sodium comes from sodium hydroxide, which is a strong base, which means sodium is a weak con acid. So here you have a weak con acid plus a strong con base. The pH of that solution will be greater than 7 because of the strong conjugate base. This is an example of anion hydrolysis. Acetate as an ion here, a strong conjugate base means that it is a strong proton acceptor. So in this case, the acetate ion is going to accept a proton from water and form hydroxide ions. So you have a pH greater than 7. Because sodium is a weak conjugate acid, it means that it is a weak proton donor, so it doesn't do anything. Okay, it doesn't donate any protons. The only example I can think of is ammonium. So we'll just go back to NH4Cl. Cl comes from HCl, which is a strong acid, which makes Cl a weak conjugate base. It will not have the strength to take a proton from water. Ammonium comes from ammonia, which is a weak base, which means NH4 is a strong con acid. As a strong con acid plus a weak con base, the pH will be less than 7. What happens, because ammonium is a strong conjugate acid, it has enough strength to donate a proton. It has enough strength to donate a proton when it's dissolved in water. So if it donates a proton to water, it forms hydronium, which drives the pH down. Okay, I think that's, just go through, I think I explained that better. And then, okay. I already walked through that. So what I would like to do